Computer programming. I mean, it's basically the language running our entire world now.
Absolutely. Everything from your phone, the whole global supply chain.
And it's the engine behind this huge AI wave we're seeing.
Right. But here's the thing, isn't it? It's this critical skill.
Uh-huh.
But we actually know very little about how our brains, learn it on a neural level.
Yeah, it's a real paradox.
Mhm.
For things like reading or math, scientists have a pretty good idea of how the brain adapts.
We do. But coding, it's different. It's modern. It's structured logic. So the question's been, when you learn, say, Python, does your brain have to build some completely new specialized thing just for code?
Or is it maybe just reusing the stuff you already have? The
Yeah.
basic tools for thinking logically.
Exactly. Is it building new circuits or recycling old ones?
And that is what we're digging into today. We're looking at some really interesting federally funded work from Johns Hopkins University.
Just published in the Journal of Neuroscience.
Right. And the mission is to figure this out. Specialized coding circuits.
Mm.
Or is the ability to code somehow
Yeah.
already baked into our existing brain hardware, just waiting to be, well, used?
Yeah, repurposed or recycled. And what's so cool about this study, what we're going to unpack,
Uh-huh.
is this idea that if you can handle basic logic, step-by-step reasoning, which, let's face it, as an adult you can,
Sure.
then you already have the core neural foundations to learn programming. Coding class. It's mostly just teaching you the new vocabulary, the syntax.
Okay, that's a fascinating angle. Let's get into it. First, maybe set the stage. Why is coding such a unique challenge for the brain?
Well, think about evolution. Our brains didn't evolve to sit and write highly structured symbolic logic,
No,
right?
definitely not. We evolved for, surviving out in the world.
Precisely. And Marina Bedney, a cognitive neuroscientist and one of the senior authors here, points this out. So many things we do now. Driving, reading, complex math, and programming. Our brains didn't specifically evolve for those tasks,
Right.
which means the brain has to be incredibly adaptable.
Okay, so when we face a new skill like coding, how does the brain adapt? You mentioned two main ideas researchers had.
Right. So the first possibility is what they call a de novo maps.
De novo, like from scratch.
Exactly, from scratch. This idea suggests coding is so specialized, so high level, maybe the brain has to build entirely new neural networks just for understanding code?
Like constructing a whole new highway system just for programming thoughts.
Kind of, yeah. A dedicated system.
Okay, what's the alternative?
The alternative is something we see a lot of support for in other areas, like how we learn to read. It's called the neural recycling hypothesis.
Neural recycling. Okay.
It's a much more efficient idea, really. It suggests you don't build whole new brain areas for these cultural skills.
Uh-huh.
Instead, you repurpose or recycle existing brain maps that were already good at something similar.
So for reading, maybe you recycle parts of the brain that recognize objects or patterns.
Exactly. And for coding, the idea is maybe you recycle the brain areas already handling logic and reasoning.
So instead of building a new highway, you're just paving over the existing logic path we already use every day.
That's a great way to put it. You're upgrading the existing infrastructure.
Okay, so that hypothesis makes intuitive sense, but how do you actually test it? You need to see the brain in the act of learning.
Right. And that's what Yunfei Liu, Marina Bedney, and the team designed their experiment to do. They needed a really clean before and after picture.
How do they set it up?
It was pretty neat. They got 22 college students, half female, half male, who had absolutely zero programming experience, none at all.
Total novices.
Complete novices, and they used fMRI, functional magnetic resonance imaging, to scan their brains.
Okay, so they could see which brain areas were active.
Exactly. They scanned them before they took any programming classes.
And then after?
And then again after they finish a full semester-long introductory course in Python.
Python, right. Super common language, known for being relatively readable.
Yeah. Good choice for this. And they didn't just show them random code. They focused on the real building blocks.
Oh, that's specifically.
The core logic structures, for loops.
Those are for repetition, right? Doing something over and over.
Exactly. And if conditional algorithms.
Which are about decisions. If this happens, do that.
Precisely. These two are fundamental to pretty much all programming logic.
So with the fMRI, they could watch how the brain activity, the patterns of neurons firing, changed after the students actually learned Python.
Yep. They could see if and how groups of neurons' population codes started to represent the meaning of that code.
Okay, let's start with the after picture. What happened once they knew Python?
Well, after the course, when the students looked at actual Python code snippets using those for and if structures, .bingo, a very specific brain network lit up.
Which one?
The left lateralized fronto-parietal reasoning network.
Okay, break that down. Fronto-parietal sounds like front and side of the brain. And reasoning.
Pretty much. It's this network heavily involved in things like planning, handling abstract rules, sequential thinking. Basically, your general purpose logic and problem-solving engine.
Like when you're doing a Sudoku puzzle or trying to figure out complicated instructions.
Exactly that circuitry. So the post-course scans clearly showed that neurons in this logic network were now actively representing the Python code. Learning to code definitely engages these general reasoning centers.
Okay, that makes sense. You learn a logical system, your logic centers get involved.
Right.
But you said the real surprise, the thing that settled the debate, was in the before picture.
That's the kicker. Before these students knew any Python syntax before def function meant anything to them, the researchers showed them something else.
What was that?
Pseudocode.
Ah, pseudocode. So not actual Python, but like plain English descriptions of the same logic.
Perfect, like writing out recipe steps. If the oven is preheated, then put the cookies in. It's the pure logic stripped of the specific programming language rules.
Okay, so what happened when these complete beginners read the pseudocode?
This is the amazing part. The exact same groups of neurons in that frontoparietal logic network, they were already activating strongly.
Wait, before the Python course? Just by reading the plain English logic?
Yes. The underlying framework for understanding that logical structure was apparently already there, even before they learned the formal coding language.
So their brains were already processing the idea of repetition, the idea of a conditional choice, using the same neural machinery that they would later use for Python.
And it wasn't just general activation. They used sophisticated analysis techniques and found that the patterns of neural activity in that region could already distinguish between the logic of a for loop, repeat this, and the logic of an if statement, make a choice.
Wow. So the ability to represent those fundamental algorithms was essentially pre-existing.
It really seems that way. The core representations were there before formal instruction.
Okay, hold on. If the basic logic structures are already represented in the brain, why do so many people find learning the syntax of Python or Java or whatever so difficult? That often feels like the main hurdle.
That's a really important question, and this study helps clarify it. Yes, the capacity for the logic seems to be built in, handling sequences, decisions.
Right.
But coding isn't just logic, it's formalized logic. It demands you follow very strict rules, the syntax of the specific cultural code.
Ah, okay.
So learning to code, based on this research, isn't really about gaining some new kind of logical intelligence. It's more about learning the very precise, sometimes finicky dictionary and grammar needed to translate your existing logical thoughts into a format the computer understands.
So the struggle is often with the translation, the specific language rules, not the underlying thinking.
That seems to be the implication. Your brain already gets the if-then concept. Learning Python is about learning to write if condition correctly every single time.
Got it. So what's the final conclusion then? Does this support the recycling idea?
Overwhelmingly, it's a really strong piece of evidence for the neural recycling hypothesis in the context of programming.
Because the basic cognitive machinery was already active before the coding class.
Exactly. The programming class didn't seem to build a new logic system. It just provided the specific cultural input, the Python syntax, and mapped it onto those pre-existing logic representations in the frontoparietal network. It recycled them for a new purpose.
That's actually quite profound. It really changes how you might think about learning to code.
It does. It demystifies it quite a bit.
Yeah. For anyone listening who's maybe looked at code and just felt completely overwhelmed, like, my brain just doesn't work that way.
Yeah.
This research kind of says, well, actually, it probably does.
It suggests the core capacity is likely already there. As Yunfei Liu, the lead author, put it quite directly, learning to code uses the same neural machinery we use for logical problem solving. And he concluded, everyone has these abilities.
Everyone. And Bedney, the senior author, really hammered this point home too, didn't she? Pushing back against that idea of coding being only for certain types of brains.
She did. She said something like, someone not familiar with coding might look at Python and feel like they'd never be able to understand it. But our studies suggest all of us have the capacity to code. We might even be born with it.
Wow. Born with the capacity to code, in a sense. Okay, so if the bottleneck isn't really our fundamental logic ability, but more about learning the specific syntax, what does this mean for, say, education? or just for anyone wanting to learn?
Well, it shifts the focus, doesn't it? If programming is mostly applying formalized logic,
Then maybe the best way to prepare isn't just drilling syntax from day one.
maybe not. Maybe the focus should be on strengthening those underlying logic muscles first.
Okay, how do you do that?
The researchers suggest that exercising that fronto-parietal network, the logic engine, is key. Building a really strong foundation in logical thinking, problem solving, sequential planning.
So practical things.
Yeah.
Like what?
Think about activities that demand structured thinking. Puzzles, obviously. Strategy games like chess.
Sudoku.
Sudoku, absolutely.
Right.
Even, they suggested, things like having structured debates where you have to build a logical argument step by step.
Ah, like dinner table arguments.
If they're logical. Even following and debugging a complicated recipe, figuring out why something went wrong requires tracing logical steps.
That makes sense. You're basically practicing manipulating complex rules and sequences.
Which is the core cognitive work of programming, just without the specific Python or Java syntax layered on top yet. You're strengthening the foundation.
So it really sounds like our brains are quite naturally equipped for this. We don't need some massive evolutionary leap to handle modern tech.
It seems we just need the cultural input, the specific language, the syntax to overlay onto the powerful logic structures we already possess. It's like learning the grammar of French builds on your innate capacity for language.
Okay, so let's bring it all together. The main takeaway from this deep dive.
Coding, fundamentally, is formalized logic. And the brain machinery to handle that core logic, distinguishing repetition from decision-making, for instance, seems to be already active in our reasoning networks before we even see a line of code.
Learning to code is learning the specific language to express that logic.
Right. It's recycling existing cognitive tools.
Which leads us to a final thought, something for you, the listener, to chew on.
Yeah.
If our brain's core logic centers are essentially pre-wired to handle complex algorithms, even before we're taught coding, well, maybe we seriously underestimate the power of the everyday logical skills we all use constantly.
Interesting point.
And maybe we should start thinking about coding structures like for loops or if statements less as some alien specialized language and more as just the natural, almost inevitable cultural expression of fundamental human reasoning itself in our modern world.